Hello, welcome to the last session of the day on forensic analysis techniques in general. So we have a mix of three techniques here. So two of them are spanning a couple of abstraction layers. So we've got some application level analysis, some file system level analysis, and also some general techniques around lookup strategies in digital forensics. So we've got a bus to catch at it's 16:45, so I have to be quite strict on time on these. So no further ado, can I introduce Harald Baier, who's going to talk about the efficiency of artifact lookup strategies in digital forensics.
So welcome to our joint paper. Mainly it was coordinated by Lorenz Liebler, who gave a talk in the previous session about APX bin. And the scope is the same. So therefore he's the main author. Patrick Schmidt was a master student of Lorenz, who originates from the Technical University of Darmstadt. My affiliation is Hochschule Darmstadt. I'm leading the DASEC Biometrics and Internet Security Research Group, and I'm also involved in this IT Research Center, CRISP, in Darmstadt. And finally, we also have a joint work with Frank Breitinger, who's also very familiar with this topic. The agenda of my talk is to give a small motivation, although the scope already was mentioned a few times in the previous session. We investigated three candidates for the lookup problem. I will highlight them in the second part of my talk. Then I will give you some insights in the requirements for the candidates and their previous and final capabilities. And then I will give you some information about extensions which we provided in our work. I will sketch evaluation and then I will conclude. So the motivation in the invited talk tomorrow was called data density. So there was this exorbitant number of some exabytes per DNA gram. We call this data overload, and what you see are two pictures, maybe the picture from some years ago and on the left side, and also the picture also some years ago, because a hard disk drive is not that common in today's investigation. But the motivation for our work is that in an ordinary case for a forensic investigation, you have some storage media, heterogeneous, but you have to deal with different terabytes of data. Terabytes, yeah. Not yet petabytes, but maybe terabytes. This is our use case. And if you think going through that for finding relevant artifacts, I think the following picture is very helpful. 1 terabyte of data, if you think of printout text, and you print it on a page where one page hosts 5,000 characters, then you have 220 million of pages. And if you look at the weight of this paper, then you have 1 million kilograms. So the motivation which you keep in mind is you cannot work with that by hand. So you have the forensic investigator. It's, for instance, this person. And then when you start, you have bulk data, and this is the haystack. And then your task is to find relevant data, and relevant data means that you have to find the needle. This is what you are searching for. For instance, the relevant question is you have different terabytes of data, and then do you find any artifacts of child abuse pictures? Then the child abuse picture or a deleted fragment of that would be the needle for which you are looking for. And then you need automated pre-filtering. And the community so far discusses about two approaches to find the needle in the haystack. The first approach is to decrease which is not relevant. So to decrease the haystack, which means reduce the haystack. Or what is in my perception, more relevant is to increase the needle, which means to help by filtering in artifacts which are candidates for those artifacts for which you are actually looking for. In this use case, approximate matching is a topic which is now, let's say, 15 years old. Yeah? And in the previous session, you had this malware analysis as one use case, and the general pipeline is, as you see now on this slide. First, you have a data set of the needles, yeah, of data for which you are looking for. Because it's a needle, it's what you're looking for, it's a blacklist. And the first phase is the construction phase, which for the approximate matching use case means that you take an input file, you extract features or blocks. A block is a characteristic block, typically. And for space conditions, you hash them. Yeah, you cannot store the whole data as it is, but you hash them. And then you insert this in this database. And database is in quotation marks because you should not think about a classical database. Yeah, in this malware analysis paper in the last session, I think it was SQLite. But in the general case, you cannot expect that it's really a database format. And we're talking about a fuzzy nature of input data. And fuzzy nature means that you cannot sort it in a straightforward way. So this is what you should keep in mind. And therefore, approximate matching. We're looking for needles which are similar to other ones. So this is where you construct your database, your data set, which you will use later on to decide if, during the lookup phase, the second phase, you have then a device, which is maybe relevant in your case. And then you proceed similar. You take an input data stream, for instance, a file, a deleted file, or a fragment. Then you extract the features again. You hash them, and then you look in your database if you find something where you think it's similar or it's exactly the same for which you are looking for. And this is the automated filtering process. But once again, we have a fuzzy nature of input data, and this means it's not that obvious how to decide about a membership. And if you take the naive general approach, you have to compare something on your seized device against all elements from your database from the construction phase. And this doesn't scale very well. So this is what we call the database lookup problem. Decide about membership, but being better than a brute force comparison. So this summarizes again. We are looking in this paper for only efficiency. We don't care about accuracy or any classification matrix. We are looking for efficient in the sense of runtime performance. In the use case white blacklisting, or one of our candidates comes from the carving use case. And we generally think that we have a large corpus with which we are dealing. And then we looked, what does the community provide? Candidates which are already somehow related to the digital forensics community, or which are so interesting that we can take them into account. Further goals, this was also already mentioned in the previous session, that we are looking for blocks which are somehow characteristic for an artifact. If you think of the identification of a malware portable executable, you have some sections where you have static file information inside, which is not relevant for a specific file. And this is what is meant by the deduplication phase within our work. And then, once the construction phase is finished, you can also think about how static is this database, or take it the other way, is it possible to add or to remove elements after the construction phase is finished? So, the candidates. 3 widespread candidates, I said. The first one is one from Simpson-Garfinkel and McCurran from the DFRWS workshop 4 years ago. And this is also used in the well-known bulk extractor tool. So this is, and one main reason we chose it is because it goes through the whole pipeline I just mentioned. The second candidate are hierarchical Bloom filter trees. This is a concept which is now about 5 years old and which we use in our software for this time. And the final one is, which is from the database community, something which has the best lookup complexity, namely a constant one. It's a hash map or a hash table, and last year at the C++ Now conference, Malte Skarupke claimed that he has the best performing hash table, which he called a flat hash map. So this was our pre-selection. So we investigated these 3 candidates, some more details on these candidates. The hash DB, or this hash-based carving from Garfinkel, actually uses a database format which is mapped in the memory in a light way. So this is the LMDB format. In the paper 4 years ago, they take 2 data sets, a small one and a larger one, which comprises about 1 million files. And it features multi-threading by design, and it's therefore read optimized. And it has a built-in deduplication, which means that Garfinkel emphasizes that he's interested in characteristic artifacts of a specific file. So he wants to prevent what we call multi-hit, or what you can call a common block, something which is shared within several files. In the HashDB, you can add and delete items after the construction phase. And for the block building, which I explain in a minute, they use a fixed sliding window. In our work, we often make use of Bloom filters. This image, if you're not aware with Bloom filters, should give you a small example how a Bloom filter works. A Bloom filter is very space efficient. So this was the reason why it is used in some approximate matching algorithms. For instance, Vasil Rusev uses it for his SD hash, for storing his SD hash fingerprint. And what you here see is you have 3 elements, X, Y, Z, and these are represented by 18 bits. 18 bits. Less than 3 bytes. And the proceeding is very simple. You insert the first element X into the Bloom filter by simply computing 3 values. Typically, it's a hash value, and then you have the index within your Bloom filter. So this means the X sets this one at this position, at this position, and at this position. And you proceed with Y and Z in the same way. But what you also see on this image is that this position is switched. The Bloom filter originally has only zeros. And when you insert an element, you switch to the 1 if the certain index is reached. So, but what you see here is that this one is actually reached by 2 different elements. And this is what the Bloom filter is not aware of. The Bloom filter itself doesn't know how often a certain position would be switched to 1. Actually, at least it was 1 element, but it can be more elements. So then later at the lookup phase, if you want to decide if a presented element W is in the set, in this set here, you simply take the same approach. You compute the 3 positions, and then you look, are there ones? Because if W is in the set, then all 3 positions must be set to 1. This is okay here. This is okay here. But at this position, you see, there is no 1, so this means W cannot be element of the set. However, if W would match, let's say, to this one, this can also happen by this Y element. So a Bloom filter has false positives. It doesn't have false negatives, but it has false positives. So when we came up with Bloom filters for deciding about membership, then this is now, I think, 4 or 5 years ago. The idea is to take a large Bloom filter, the root Bloom filter, decides about the actual membership. But then you don't know which individual file is it, and to come up with the individual file, you have to traverse this Bloom filter, and in these leaf nodes here, you have a small set of files which you can compare by hand. So this is the main idea of the Bloom, of the hierarchical Bloom filter tree. So, and this concept was implemented 2 years ago by some people from the University College of Dublin and with Frank. And this is some sort of proof of concept. This works. Interesting for the lookup complexity is that instead of ON, N is the number of elements in the data set. This is decreased to the log of N, which is okay, but you have false positives. I mentioned that already. And one really problem with Bloom filters is inserting or deleting elements. Inserting is somehow possible, but deleting is not possible because you don't know if the one in the Bloom filter is also set by some other element. So you cannot really delete elements. And this is what you should keep in mind when you later on talk about the evaluation. The next slide is some information about the flat hash table. Once again, a hash table itself has a constant lookup complexity. So at a first glance, you would say you must make use of a hash table, but you're not aware how long does it take to construct it, what are the memory consumptions, and things like that. The hash table of Maldeska-Rupke has different features, which makes it very attractive for our purpose. One is that due to the Robin Hood hashing, you can ensure that an element actually is close to its ideal position. And it has no false positives. Okay. That you have a rough understanding of the three candidates. They are either very attractive, like the flat hash map, or they are already discussed in the forensic community. I will show you only a very short part of what we did in the requirements and capability section. But what is important in our perception is that you actually have discriminative blocks. Or to put it the other hand, a multi-hit is a block which appears frequently in different files. For instance, parts of the file header. Or if you have a popular software library which is statically linked to some executable, then you will find this code or this information in different files, and this is not really discriminative. So what we want to avoid is multi-hit, and this is also supported by this HashDB approach of Garfinkel. So actually this is the core result of our capability and requirements analysis. What you see in the left column are the main requirements and some further information. You see the storing technique, for instance. Block building means how to extract these characteristic blocks or the blocks from a given file, from a given artifact. And the semantics is as follows. If a cell is green, then this means originally this was not part of this concept, but we successfully implemented it or provided a concept and implemented it. For the block building, this was not really complicated because we used it for our different approximate matching approaches. The block hashing you see is in this row. An important aspect to our perception is that at least at the lookup phase, it's possible to perform multi-threading, simply for performance reasons. You don't want to wait for hours or days for the result, but the real time should be decreased by some parallelization. We have multi-hit handling, and what you see here, actually this should be a red color. This is somehow changed here. What I already said, that for the hierarchical Bloom filter trees, it's hard to insert elements. This means this partially. And the caret means that it's practically impossible to introduce a deletion in the Bloom filter after the construction phase. This is practically not possible without losing the good properties of the hierarchical Bloom filter tree. And you have some more information. If you're interested, you can have a look at the paper. So which extensions? I just will sketch it in one slide and give you an information for only one item of that. The multi-hit prevention was not possible for the hierarchical Bloom filter tree or for the flat hash map. We provided the concept and also an implementation for that. What you here see is that for the hierarchical Bloom filter tree, we have two concepts, and we evaluated that, and the global filter-based one was the better one. The parallelization of block building, I will give you a short insight in the actual problem and the concept. I talked about characteristic blocks which you want to extract. So think of this as a file which has 8 characteristic blocks. Then you have some algorithm which finds C1 as the first characteristic block. Then you find this boundary, then you go to C2, and so on. If you have no parallelization, you start at the beginning of the file, and here you will end up. So the problem is, if you now want to parallelize this, then if you have 4 threads, you take 4 segments of the file, but then if you start at the beginning, it's no problem. But if you start at this position here, then you don't know where is the next boundary for the characteristic block. But that's not really hard, because you can go then to the next point. You start there, and then you go as long as you're in the next segment. So actually, from the conceptual point of view, this is not really hard, and therefore we integrated that in our implementation. One sample runtime for that. We have the real time, the wall clock time in the first row, and the processor time in the bottom row. And what you see here is the wall clock time if you only make use of one thread for a data set of about 2 gigabytes is roughly 44 seconds. The CPU time is a bit lower. But actually what is of interest for us, the real time decreases to less than 1/3 if we make use of multi-threading. So actually this works, and this decreases the overall lookup time. Then finally we provide some evaluation with respect to different aspects. The first one is the memory consumption. The larger the data set is, also the larger will be the memory consumption. So this is one important aspect, and this shows that the flat hash map and the hierarchical Bloom filter trees are approximately the same. The Bloom filters are a bit better for the memory footprint. Then the runtime of the construction phase, we evaluated in both modes, if we only have a single thread or if we have more threads. It had been 8 in our evaluation, and the same we did for the deduplication and also for the lookup phase. And I will show you only some results for the runtime performance of our lookup of the lookup phase. What you see here, this is only runtime measuring. The runtime is here on the vertical axis, the runtime in seconds. And what you see here is the question: how does the runtime depend on the matching of the artifacts? And what we did is we compared identical files against each other, and then you have this picture here. And you see that the HashDB is the slowest one if you compare full identical files. So then this number here means that if per design the seized information is only 75% of the original ones, then you have a decrease of the runtime of the HashDB. This is due to pre-filtering, and so on. So interesting here is that if we look at the actual practical relevant picture means that we have a multi-threaded use case, and you see that the gap between the hierarchical plume filter trees and the flat hash map is not as large as you may expect, because the theoretical runtime of the plume filter tree and the flat hash map is log n to constant, and the HashDB is much slower. And this is the overall picture, where we did some assessment of the different aspects. And if you go through the different columns, you see that the HashDB has all the features before. We implemented that for HBFT and the flat hash map. But what you see then is in the actual system, which you are interested in later when finding the needle, that the flat hash map is the best one, the hierarchical plume filter tree is the second one, and the HashDB suffers from some deficiencies. This is the conclusion. Flat hash map outperforms both other candidates. The hierarchical plume filter tree is per design as it is. Yeah, we cannot improve it without losing its original conceptual advantages, and therefore we will make use of the flat hash map in our memory carving engine. Get in contact if you're interested in this or APXBin or similar things. If you're still at junior level or so and you want to do an internship at CRISP, you're welcome to contact us. Thanks.
Any questions?
Hi, thanks very much for your talk. I'm just wondering, how does this approach scale when the scale of files that you're looking up grows exponentially? So, like, you know, what are the limits to the advantages here, if indeed there are any?
Actually, the scaling question is a good one. You have these theoretical estimations, at least for the plume filter trees, which should be logged during the lookup phase. We're only talking about the lookup phase, and a constant one for the flat hash map. In our evaluation, we made use of a 2 gigabyte data set. So we have to increase this more. But my guess is that the data set must become really large, that this gap becomes larger between the plume filter trees and the flat hash map. Actually, for the HashDB, this is a database approach. I'm not aware of any theoretical scaling behavior.
Perfect.
Any more questions? Okay, let's just ask you one. Just one question. Yeah. Where, in terms of these different techniques, where are we in terms of, I guess, technology readiness levels? You mentioned bulk extractor. Are these in commercial tools? Are these just implemented in other circumstances?
With respect to this question, you should make use of this HashDB. Yeah? And this is what in the keynote this morning was, don't keep in your academic world, go out and convince practitioners to make use of that. The HashDB is rolled out as part of the bulk extractor. And the other thing is somehow we provide this on GitHub, so feel free to make use of that. And actually, I think this is a general remark that we don't really look at the impact for practitioners. Yeah. But you can use it. It's on GitHub. Yeah. But I'm not sure to say anything about ready for market.
Okay, no, that's great.
It's academic software so far.
Okay, thank you again. It's fantastic.